Hello class, welcome once again to CHM 312 class. We shall begin to discuss a new topic today, and for a couple of weeks we shall be discussing this topic, electrochemistry. I believe you all have heard the word electrochemistry before, and you have some background knowledge of this topic. But for the sake of this course, I'm going to begin from the very basic so that we can flow along together properly. We shall look at from the basics and then we shall move on to more advanced parts of this subject. We shall discuss Faraday's law, we shall discuss next equation, and so many other topics under this topic, electrochemistry. Also, I would like to ask you to get a good note and paper that you use to jot down things that will be discussed in this course, because I'm going to be discussing so many and solving so many questions that might not be fully solved on the slide, but if you are writing, if you are following what I'm teaching, you'll be able to put it down in a way that you understand better on your notes, such that when you need to prepare for this course, you'll be able to pick up those notes and revise them. So I encourage you, make sure you are writing while you are listening to this lecture. So let us continue. Let's start. So now, first we need to understand the term oxidation number, because throughout this topic, we shall be mentioning the word oxidation number very frequently. So it is very important for you to understand what the concept of oxidation number is. So now, what do we call oxidation number? Oxidation number are a convenient way of determining if a substance has been oxidized or reduced. So we use this concept oxidation number to determine whether a substance has been oxidized or the substance has been reduced. These numbers are assigned arbitrarily to atoms and are equal to the charge the atom would have if its bond were purely ionic. So the meaning of that statement is this number is just very similar to what we call valence number. That is the bonding number, the amount of, if this number was purely ionic, the amount of electrons it would have lost or it would have gained is what we write arbitrarily as the oxidation number. Now, some very important things you need to know is that for all free atoms in elements, they have an oxidation number of zeros. Whenever you see a free atom, if I write a chemical equation and I put an atom without any charge, that's what I mean by a free atom. You can see this is a sodium element now. It's a free atom of sodium without any charge. It means that the oxidation number would be 0. This magnesium also would be 0. This is hydrogen molecule. Hydrogen molecule here is not carrying any charge, so therefore it's going to be what? 0. This chloride molecule, this is going to be 0. This phosphorus is also going to be 0 because they are free atoms. So whenever you see a free atom in a chemical equation that does not have any charge on it, then the oxidation number is 0. Number 2 is that for simple ions, that is ionic compound, when you have just simple ions, the oxidation number is the same as the charge of the ions. When I have simple ions like potassium ion, you can see it is carrying a plus sign. It means the number will be +1. We don't need to write 1, that's why it's just carrying a plus. If you have 2 plus, it means the oxidation number is +2. If it has 3 plus, the oxidation number is +3. 3 minus, -3, 2 minus, -2, and then you have your fluoride minus, which is -1. So that is 2 very important things to know. This will really save you a lot of stress. Okay, for covalent compounds, the covalent bond are changed into ionic bonds by assuming that the bonded electrons are on the more electronegative atom. Now let's see what we mean by that. What if the compound, the elements or the compound we are talking about, what if it is not ionic compound like we have in the previous point that I made where I said we can just have a fluoride ion carrying a negative charge, which means the oxidation number will be -1. What if it's a covalent compound? How do we approach such situation? Let's see. For example, we know that elements that are in group 1, they do have a +1 oxidation number. Elements that are in group 2, they do have a +2 oxidation number. Elements that are in group 17 is also known as group 7, so don't mix it up. Group 7 is also group 17. The reason why we are calling it group 17 now is because we've counted each groups, including the transition metals on the periodic table, and there are 10 of them. So when we move from group 1, group 2, we count all 10 transition elements, then we count group the next one up to group 7, which will now be bearing group 17 instead of group 7. So all group 7 elements have oxidation number of -1. Oxygen has oxidation number of -2. Hydrogen have oxidation number of +1. Now, there are some exceptions you need to know. Oxidation number for group 7, that's the halogen family, fluorine, chlorine, bromine, iodine, is -1. But it is true only to halogen without oxygen in it. So whenever we have a halogen that has an oxygen, for example, if you're having a reaction between fluorine and oxygen, the charge of halogen will no longer be -1. Is that okay? If you have a reaction between chlorine and oxygen, the charge of the halogen will no longer be -1. So you need to take note of that exception. Also, oxygen is -2, but the exception is that oxygen is -1 for a peroxide and it's +2 when it is in a reaction with fluorine, F2O. So oxygen can also have -1 and +2. I said -1 for a peroxide. Peroxide is like what we have in hydrogen peroxide, which is H2O2, is a peroxide, hydrogen peroxide. So, and this is for a reaction with fluorine, oxygen will also have a +2 oxidation state. So, but besides from these two cases, the oxidation state of oxygen will always be -2. For hydrogen, the oxidation state is always +1, except in metal hydride. Whenever it's in a metal hydride, if you have a metal here, for example, if this is copper hydride, if this is zinc hydride, whenever it's a metal hydride, the oxidation state of hydrogen becomes -1 instead of +1. But these exceptions are very, very uncommon. So in most questions that you'll be seeing or most situations that you'll be encountering, these values are always correct. In most cases, you'll be meeting. But when you come across situations where you have these exceptions, you will know how to find your way out of it. Because in the case of this fluorine, F2O, you can see the fluoride now, the oxidation state of fluorine is going to be -1, and there are 2 of it. We are going to see how to calculate that in the next coming slides now. So you'll be able to find out that oxygen is still +2, even from here. But this stereotype idea of oxygen having -2, it's only in this kind of situation that it is no longer acceptable. But in every other situation, oxygen will always be -2. So what's the summary of what I'm saying? If you have a covalent compound, in order for us to know the charges, the oxidation number, we need to use these standards. That means if there's any group 1 element there, we know the charge is going to be +1. Example of a group 1 element is what we have, sodium. Is that okay? Sodium, potassium, those are group 1 elements. They will always have a charge of +1. So because we already know that, we can find the charge of any other element or atom or molecule that is in that compound. So for group 2, example is your magnesium, calcium. Is that okay? Those ones are going to have +2. Your group 7, which is also group 17, we have -1, which include your fluorine, chlorine, iodine, bromine. Then your oxygen is -2, hydrogen is +1. Okay, now, in a neutral molecule, the sum of the oxidation number of all atoms are equal. So whenever the molecule is neutral, the sum are always equal, and it will be equal to what? Equal to 0. That's so whenever you have a neutral molecule here, for example, this is a disodium oxide. If you're having a disodium oxide like this, the total, by the time you sum up the oxidation number, it must be equal to 0 because it is a neutral molecule. You can see also we have here, this is a boron oxide. You can see in this boron oxide, you can also see that by the time you sum them, the oxidation number will always be equal to 0. So put that at the back of your mind. So let's see, how can I find out the oxidation number of sodium in this case? Let's assume I don't know sodium belongs to group 1 on the periodic table. But at least one thing I know is that the oxidation state of oxygen is -2. Okay? I can determine the oxidation state of sodium. Let's see how to determine that. How many sodiums do we have here? 2. So I say 2 sodium plus how many oxygen? 1 plus oxygen will be equal to 0. Because I already said in a neutral atom, the sum of the oxidation number are always equal. And they are equal to what? 0. Now, so this is 2 sodium plus, I don't know what the oxidation state of sodium is. So that's what I want to find out. Plus, I know the oxidation state of oxygen is always -2. Okay, so this is -2 equals 0. So if I do the math, I'm going to find out that, okay, let me do the math for you so that you can see it more clearly. So if this is 2 sodium, let's assume, let's take that to mean 2x. So this will mean 2x minus times plus is minus, 2x minus 2 will be equal to 0. 2x minus 2 will be equal to 0. So it means that 2x would be equals to, take -2 to the other side, it becomes +2, which is 2. So divide both sides by 2 to get x. So x will be equals to 2 divided by 2 is 1. And that will be +1, of course, because this -2 came to the other side to form +2. Okay, when minus move across the equality sign, it becomes plus. So this is +1. So it means sodium, which is N, will be equals to +1. So this is how we arrived at +1 value. I believe that is very clear. Okay, having said that, let's see another one. Okay, let me pick SO3. SO3 now, we have 1 sodium plus 3 oxygen will be equal to 0 because it's a neutral atom. How do I know it's neutral? There is no charge. If I saw SO3 2 minus now, it's a different case. It means it is carrying a charge. But when I see just SO3, it means it is carrying no charge. And whenever it's carrying no charge, the sum of the oxidation number will be equal to 0. So I have 1s plus 3 oxygen to give me this. 1s, which is what I'm looking for, I don't know, plus, I know oxygen is -2, so that's 3 minus 2 is -6. So take -6 to the other side, it becomes +6. So very simple mathematics. So it means the oxidation state of this sulfur is +6, while oxygen is -3. Let me pick another one from this end. You can always play around and work your way around every other one that I've provided here. But let's see this one. In the case of this one now, I have CH4, which is methane. I have 1 carbon plus 4 oxygen to equal to 0. I don't know the oxidation state of carbon, but I know hydrogen is always +1. So I can say 4 plus 1, 4 times +1, sorry, which give me 4. Take +4 to the other side, it becomes -4. So the oxidation number, this N here is just telling me the oxidation number. I just need to replace, this should be carbon. This should be carbon if I wanted to follow the same method I've been using for others. So carbon is equals to -4. So the oxidation state of carbon is -4. I believe that's very clear. Now let's see a little bit more complex example. Let's see H2SO4 sulfuric acid. This is 2 hydrogen plus 1 sulfur plus 4 oxygen equals 0. I know hydrogen is +1. So 2 into bracket +1 plus 1 sulfur, which is what I'm trying to look for. The oxidation state of sulfur is what I don't know. I know the oxidation state of oxygen to be 4 into bracket -2 equals 0. So if I do the math, 2 times 1 will be 2 plus sulfur, 1 sulfur, which is just sulfur here now, so that's S, 4 times minus 2 is minus 8. Minus times plus is minus, so this is minus 8. Sorry, it's minus 8, which is all equal to 0. All equal to 0. So this will give me, this is S. So I can take 8 to the other side, it becomes plus 8. Take 2 to the other side, it becomes minus 2. So S, which is sulfur, S, which is sulfur now, will become, take minus 8 to the other side, it becomes plus 8. So this is 8. Take plus 2 to the other side, become minus 2. 8 minus 2, which is equals to plus 6. Okay, so that is how we arrived at the value plus 6. How we arrive at the value plus 6. So you can lay your hands on other examples that I have put here and make sure you are very good at it, because you will be needing this skill while solving a more difficult question. I will most likely not give you a question to look for the oxidation state of anything of this nature, but while you are solving more difficult questions, you are going to have to utilize this skill in answering the question. Okay, another important thing is that in a molecular ion, that is, the first one I talked about was in a neutral atom. Now let's look at in a molecular ion, the sum of the oxidation numbers of all atoms in the formula unit equals the charge on the ion. Now in this case, it is not neutral. You can see it is carrying a charge. This is Cr04 minus. You can see this is Cr2O7 2 minus. This is MnO4 minus. This HSO4 minus, ClO2 minus, C2O4 2 minus. So all of them here, they all carry charges. They are molecular ions. They are non-neutral atoms like we have in the previous examples. So in this case, what do we do is we sum them. The sum of all the oxidation states of the atoms in the formula unit will be equal to the charge of the ion. So in this case, it means the sum of all this will be equals to minus 1. The sum of all this will be equals to minus 2. The sum of all this will be equals to minus 1. The sum of this minus 1. Sum of this minus 1. Sum of this minus 2. So it's just as simple as that. In the previous one, the sum is always equal to 0 because it is a neutral atom. So let's see how that works now. Here, I have 1 chromium plus 4 oxygen to be equal to minus 1. I know oxygen is minus 2, so I can find chromium. Minus 2 times this will give me minus 8. Take it to the other side, come plus 8. So minus 1 plus 8 is plus 7. The same thing here, 2 chromium plus 7 oxygen equals the charge, which is minus 2. If I do the math, I'm going to have 7 minus 2 times minus 2 is minus 14. Take minus 14 to the other side. It becomes minus 2 plus 14. Minus 2 plus 14 will be equals to plus what? Plus 12, of course. Plus 12. You can see that I have 2 at the back of my chromium here after taking this off. So I'll divide both sides by 2 so that chromium can stand alone. Therefore, Cr, which is chromium, will be equals to 6. When I divide this by 2, I'm going to get 6. So make sure you have a pen and a paper and you are solving out these things yourself to see what we are talking about. So let me just take this last one. This will be 1 hydrogen plus 1 sulfur plus 4 oxygen equals minus 1. Of course, that's the charge. So 1 hydrogen we know is plus 1. Oxygen we know is minus 2 equals minus 1. If you do the mathematics correctly, you will end up with plus 6 as the oxidation state of sulfur. Okay, so that is all about oxidation number. If you do not understand oxidation number well by now, make sure you go back to those previous slides, understand it properly, because we'll be relying on that knowledge as we move ahead. Now let's look at half equation and redox reaction. Half equation and redox reaction. Half equation are equations which shows how electrons are accepted or donated in a chemical reaction. So when electrons are accepted or donated, we use half equation to show the equation for each one, that is the acceptance and the donation of electrons in a chemical reaction, are shown using half equations. Now, when a substance is oxidized, take note of the word oxidized. Whenever a substance is oxidized, electron is donated. If a substance is oxidized, electron is donated. If a substance is oxidized, electron is donated. That is, E minus, which is electron, is written at the right side equation. So you write that E minus on the right side. I wouldn't want you to memorize it anyway. I'll show you how, I'll explain it so that you could understand it. But this is another way to see it, is that whenever electron is donated, E minus is written on the right side of the equation. And when a substance is reduced, electron is received, and E minus is written as on the left side, as the left side of the equation. So that is what we mean by oxidation and reduction. So another way, there's a common statement that says oxidation is loss, reduction is gain. So we call it oil rig. This is a very common acronym in electrochemistry, oil rig. Oxidation is loss of electron, reduction is gain of electron. So whenever you remember the word oil rig, oil is oxidation is loss, reduction is gain, that's rig. So whenever a substance is oxidized, electron is donated, that means lost. Electron is being given out. And whenever a substance is reduced, it means that electron is being received, that means electron is being gained. So that's what that means there. So now let's see some simple half equation. Simple half equation. State the change of oxidation number and write the half equation. So we need to state the change in oxidation number and then we write the half equation. Let's see reaction one. This is sodium moving from just sodium to sodium plus. Oxidation number change is from sodium. I told you sodium here is a free atom, and I told you every free atom have oxidation state of 0. So this is moving from 0 to +1. From 0 to +1. So we are saying this, what has occurred here is oxidation. What has occurred here is oxidation. Now you might say, but the oxidation number has increased. So this is supposed to be gain. It has gained electron. No, in chemistry it is the other way around. Whenever a substance loses an electron, it carries a positive sign. So when a substance loses 2 electrons, it carries 2 positive signs. When it loses 3 electrons, it carries 3 positive signs. So, but when it gains electron, it carries a negative charge. So that plus minus is not the same with mathematics, okay? So in this case, whenever a substance moves from 0 to +1, it has actually lost 1 electron. It has lost 1 electron. So therefore we say it has donated electron, and then this process is oxidation. I believe that's clear. Another way to see oxidation is, besides from saying oxidation is loss of electron and reduction is gain of electron, whenever oxidation number increases, it is still oxidation. So whenever you see something going from 0 to +1, that means the oxidation number has increased. We say it's oxidation. Although what has really happened is that electron has been lost. In this case, oxidation number also increases, so we also call it oxidation. But when oxidation number decreases from +2 to 0, then we call that reduction. It has actually gained electrons, but the oxidation number in terms of figures has actually reduced. Okay, so that's a simpler way to remember the concept of oxidation and reduction. So this is 0 to +1, we said that's oxidation. How do we write the half equation? We say sodium, which is this on the left, reacts to give sodium plus, which is this, plus E minus. Don't forget, we said whenever there's oxidation, E minus is written at the right side. You can see this is the right side of the equation. So we just add E minus, and that is the half equation for this reaction. Okay. For this one, you can see it. Magnesium has moved from 0, which is a free atom, to magnesium 2 plus. So this is also oxidation. You can see oxidation number is increasing, and of course it has lost 2 electrons. So we write this by putting E minus on the right side. But this time around, we are going to put 2E minus because 2 electrons were lost. So we put 2E minus on the right side, showing that it has what? Lost electron. But another better way to remember this, instead of remembering right side, left side, oxidation or reduction, is just to say, if you want to show oxidation, you have Na, for instance, in this case, to give you Na plus E minus. I would note that this E minus should be here and not here. Why? Because it is supposed to balance up each side, meaning that E minus here means minus times minus and plus will cancel each other out so that this part and this part become equal. This place now, I put my 2E minus here because I have 2 plus here. 2E minus here means 2 minus plus 2 minus 2, that's 0. So it will also what? Balance up again. Is that okay? So that is the idea. Once you put that in mind, you wouldn't have any need to memorize whether you are putting E minus on the right or on the left. So for aluminium 3 plus, you can see it's going from 0 to 3 plus. So if I want to write this, I write aluminium. Obviously, I know I won't put my plus 3E minus here. I'm putting 3 here because there are 3 electrons that were lost. I won't put my plus 3 minus here because if I put my plus 3 minus here, it won't be balanced because what I'll be having now is minus 3 on this side plus 3 on this side, which is not what I want. I want both of them to be equal. So by doing so, I put my 3 minus here, which means 3E minus, which means this plus 3 minus 3, which is 0, and this is 0. So it means they are balanced. So that's a better way to think about it. So for copper, copper moved from 2 plus to 0. You can see this is a neutral atom, so it is 0. This is a charged molecular ion, and this is plus 2. So plus 2 to 0 is reduction because electron is being gained. And also, you can see that it is moving from a higher number to a lower number. So this is reduction. So Cu2 plus. On this case now, I won't put my plus 2E minus on the right. I'll put it on the left because you can see this is where I have a charge, 2 plus. So therefore, if I put plus 2E minus, this is 2 minus, plus 2 minus 2 will be 0. So this is 0, this will become 0. So that is how to commit that to memory. All right, so we can still see more. This hydrogen moving from this H2 to H plus, irrespective of having H2 here, as long as it's a neutral atom, the oxidation is going to be what? 0. And this is H plus, the oxidation will be plus 1. This reaction is oxidation, of course, and it's moving from 0 to plus 1. And then when I want to write it, look at, this is where the 2 that is here now comes in. This is H2, we react to give, instead of saying H plus, it can be H plus because it will be balanced. There are 2 hydrogens here, so I'll say 2H plus, instead of saying E minus, because of course, there are just 1 electron here, so I could have just said E minus, but because this one is 2, meaning that 2 times plus here will be 2 plus. To neutralize it, I will also need 2 negative charge, so that plus 2 minus 2 equals 0. So this is 2 times minus times E minus, so that is 2E minus. I believe that is clear. If you see in this case, the same thing is happening here. This is Cl2 to give you Cl minus. Oxygen is moving from here from 0 to minus 1. Now, this is not oxidation because minus 1 is in terms of number now. You can say from 0 to minus 1 is moving from higher number to a lower number. So it is reduction. But actually, in real sense, what is happening is that it has gained 1 electron. So this is reduction. We have Cl2 plus. Now, there's only 1 electron that was being gained. So I should have said just plus E minus, okay? But that wouldn't be the case because if I say plus E minus, this will give me, to react to give me Cl minus. Is that not so? But chlorine here, there are 2 of it. So to balance up that, it means I must put 2 here to make this one 2 chlorine. If I put 2 here, automatically this becomes 2 minus. I have 2 minus on this side, so I must also balance it with a 2 minus on this side. And how do that happen? I also put a 2 before my E minus. Think about it. It's very straightforward. So the same thing is what I can see here. Let me just use this last one as an example. Look at lead, Pb4 plus to give me Pb2 plus. Now, if you see lead 4 plus now, this give me plus 4 to plus 2. Of course, this is reduction. Something moving from 4 to 2 is reduction. So it means PB4 plus will be plus 2E minus. Can see? Don't make a mistake of saying, okay, this is moving from 4 to 2, and then maybe I put 4E minus. No, no, no. This is not a guesswork. What we are trying to do here is balance charges. It moves from plus 4 to plus 2. It means PB4 plus will be plus 2E minus to give you PB2 plus. This makes sense because 2 times minus will give me 2 minus. Is that okay? Minus 2 or 2 minus, whatever case. And this is 4 plus. So plus 4 minus 2 will give me plus 2. And see that it is balanced. But if I put 4 here or whatever I put here, it won't balance up to plus 2. I want you to give me 2 plus at the end of the day. So it will be 4 plus 4 minus 2 to give me plus 2. So that's how we arrive at these values. Just get your hand on some other examples here that I did not touch and see how we arrived at the half equation. Now, when it comes to the reaction involving molecular ion, the overall charge has to be balanced in such order. Now, take note of that. When it comes to reaction that involves molecular ions, that is, when they have charges, they are not neutral molecules, they are molecular ions, the overall charge has to be balanced in such order. Now, let's see. Number one, you write a skeleton half equation. Determine the reaction, whether it's oxidation or reduction, using the oxidation number. Like we have been doing, you determine, is it moving from higher number to lower number, from lower number to higher number? So we'll write out a half equation. Now we'll balance the charge by adding electrons at the appropriate side. We balance charges by adding electrons like we did in the previous one, plus 3 minus, plus 3 minus, appropriately to make sure that charges are balanced on both sides of the half equation. Now we balance the number of atoms other than oxygen. So if there are atoms there that are not oxygen, you balance them. We shall see that in an example. Based on the changes in number of oxygen, write the number of water molecules formed or used. So if there are cases whereby we have changes in oxygen, that is, oxygen changed, oxidation also has to do with the addition of oxygen to something. So when something moves from having 2 oxygen to having 3 oxygen, oxidation has also occurred. So, but we don't add oxygen to balance up such equation. What we do is we add water to make up for the oxygen formed. It will be clearer when we solve the examples. So now, from the number of water molecules formed or used, write the number of hydrogen ions required. So when we write water, automatically we have added hydrogen to one side of the equation. We must balance it by adding hydrogen ion to the other side. For those of you that are not too good with electrochemistry before now, these basics of electrochemistry, what I'm talking about now might be very strange to you, but when we solve questions, it will make some more sense. Now let's see some half equations and let's see how these things can work. What we just talked about, we are working with half equations. Now, don't forget, all these things we are still doing are preliminaries. These are half equations. In a real question, I will be giving you a full equation. You are the one that will now solve them based on half equation and so on. So I'm solving them based on half equation now just for clarity purpose. Now, see this first one now. We have ClO3 minus reacts to give you what? Cl minus, that is chloride. Now, changes in oxidation state. First, we need to check for the changes in oxidation state. What are the changes? What are we going to be considering here? Is chlorine. We are considering chlorine, not oxygen. You can see there's no oxygen on the other side of the reaction because this oxygen here is not the one that's, that has really changed here. Oxygen is missing on this other side. We shall balance that based on what we discussed about the steps. Now, but how do we now know what is the oxidation number of chlorine? Then we use the knowledge that we already have before. Now, I say we can just call chlorine X, okay? And then say plus, what is the oxidation state of oxygen? Oxygen here is -2. Oxygen is always -2. So oxygen here is -2. There are many oxygen there? 3. So -2, put 3 outside, that's times 3. is equal to, because this is not a neutral atom, the sum will not be 0. The sum will be equal to the charge, which we've discussed in previous slide, and the charge here is -1. So it means here now I'll be having x minus 2 times 3 is -6. Minus times plus is still minus, so this is -6. -6 is equal to what? Is equals to -1. So this is going to be equal to x now will be equals to, take -6 to the other side, it becomes +6. So this is -1 plus 6. -1 plus 6, of course, is equals to +5. -1 plus 6 is +5. So it means the charge, the oxidation number of chlorine is what I'm concerned with here now. So the oxidation number of chlorine is what I've gotten here to be +5. It has moved from +5 on this side of the equation to the other side now. What is the new charge is -1. I don't need to solve for this because chlorine is standing alone and it is not a free atom. If it's just ordinary chlorine, this will be 0. But because it is carrying a charge, this will be -1. So the change in oxidation state for chloride now is +5 to -1. Is this oxidation or reduction? It's simple to know. We are moving from a big number to a small number. It's reduction. Whenever the oxidation number is reducing, we call it reduction, okay? But what has actually happened in reality is that it has gained electrons, okay? It has gained electrons. So, but the next thing to find out now is that what is the difference in the oxidation state? Now, this is +5 to -1. What's the difference between +5 and -1? Difference is +5. Difference means minus, right? +5 minus -1. The implication of this now is that I have +5. Minus times minus is plus. So that's +5 plus 1 is equals to what? 6. So the difference between +5 and -1 is 6. So it means oxidation difference is 6. So 6 electrons at the left hand side of the equation. So the meaning of that now is that the number of electrons that has actually been gained is 6, since that's the difference between the oxidation state. So how do I now balance it? Is that I add 6 electrons to the left hand side because it is what? Reduction. If it's oxidation, I'll add it to the right hand side. Don't forget we said that before. So I'm adding it to the left hand side because this is where I have +5. The oxidation state here is +5. The oxidation state here is +5. So if I have +5, this is 6 times minus, this will give me what? -6. So +5 minus 6 is -1. So it is balanced. You can see, but if I put this one here now, this becomes +5 and this one becomes -1, -6, -7. That's not balanced. So it is correct for us to put the difference in oxidation state, that is the electrons that were gained, on the left hand side. So if you are able to commit to memory that for oxidation you put on the left hand side, then fine. But if you are not able to commit it to memory, it's better that you understand how we come about putting it on the left hand side to balance the charges. This is +5. This is 6 times -1, that's -6, +5 minus 6 is -1, which is balanced with the other side of the equation. So 6 will be here. Now, it means we balance the charges, but we are not done. We could have just left it like this and say, yes, we are done, but we are not. Why? Because you can see on one side of the equation, I can see oxygen, but on the other side of the equation, I can't see oxygen. So I need to balance up the oxygen atom. Now, from the previous slide, you saw that when we want to balance up oxygen, we don't just add oxygen to the other side. No, we add it in form of water. And then we balance up that water by adding hydrogen ion on the other side of the reaction. Now, let's see how to do that. How many oxygen do I have here? 3. To balance up those 3 oxygen on this end, I will add 3 molecules of water, because in 3 molecules of water, there are 3 oxygen molecules. Can see that? Because this is oxygen times 3, that's 3 oxygen. So it means by adding 3 molecules of water, I have balanced the oxygen atom. But I've created another problem, which is now I have hydrogen on this side of the equation and I don't have hydrogen on this side. So how do I balance the hydrogen on this side? Is by adding hydrogen ion, H+. Is that okay? Adding hydrogen ion to the other side of the reaction. So adding hydrogen ion now, which is H plus, meaning that how many H plus will I add? Because I added 3 water. How many hydrogen do I have here? 2. 2 times 3 is 6. So I must add 6 H plus to the other side of the reaction. So the final half balanced half equation would be H plus 6 of it plus ClO3 minus plus 6E minus to react to give Cl minus plus 3H2O. So this is what will be expected of you if you are solving for a half equation. So if you find yourself in an examination and then you need to solve an half equation to balance it and it contains oxygen, you balance that oxygen by adding water to the other side, and then you balance the hydrogen here, you multiply by the number of water you added, which is 2 times 3, which is 6, and then you balance it by adding a hydrogen ion on the other side. I believe that is clear. You can see another one. I'm going to solve this second one. I would expect you to sit down and ruminate and understand how the third one was being solved. Okay, so CrO42 minus to give you Cr3 plus. So I can see obviously that this one has moved to +3 here, but that's chromium now. So what is the oxidation state of chromium in this second side is what I don't know. So I need to find out. So how do we find out? The same way we say chromium, I can just call it X, or you will write chromium itself, anything you prefer, plus how many oxygen do I have here? 4. What's the oxidation state of oxygen? Is -2, and I have 4 oxygen, so that's times 4 is equal to, will it be equal to 0? No, because it's not a neutral atom. You can see it is carrying a charge, and the charge here is what? -2. Good. So it means I have X here now plus, okay, let's still leave this. This will be -2 times 4 is -8. Minus times plus is minus, so this will be -8. So I don't need to put plus again, so as to save steps. So this will be -2. So X will therefore be equals to what? Taking -8 to the other side, I have -2 plus 8. -2 plus 8. -2 plus 8 is +6. -2 plus 8 is +6. So it means that chromium here has the oxidation state of +6, and it moved from +6 and it came to land on +3. It means as it increased or reduced, it has definitely reduced from a higher value to a lower value. So it is, again, it is reduction, because it has reduced, oxidation number has reduced, but in reality what happened is that it has gained. Is that okay? It has gained electron, but in terms of numbers, it has reduced. So it's better to just know reduction in terms of number, but always have it at the back of your mind. The chemistry behind it is that even though the number is reducing, what is happening is that it is gaining electrons. Now, so let's see the difference. Difference is 6 minus 3, which is 3, okay? When we say difference here, what we are concerned with is not whether it's +3 or -3. We are just concerned with which, even if I had 6 here and I had 3 here, don't tell me 3 minus 6 is -3. No, the difference is still 3, okay? Whether big in front or small at the back, the difference is still 3. So we are not concerned with which one comes first. We just want to know what's their difference. So the difference is 3. Therefore, we know we are going to be adding 3 electrons. Because this is reduction, again, we'll be adding towards the left-hand side. And as I said earlier, you don't need to memorize it. It makes sense if this is +6 and we're adding 3 minus to this place. It means it is +6 minus 3, which is +3. You can see it is equal to the other side. So that makes sense. Now, oxygen is not balanced. We have balanced the charges now, which is the oxidation number. Now we need to balance the atoms, which is oxygen. Oxygen is on this side. How many of it? 4. So we add 4 molecules of water. Automatically, we have additional 8 molecules of hydrogen now on this side. We balance it by adding 8 molecules of hydrogen ion to the other side. So do the same thing for the last question, for the last example, and ensure that you understand it fully before you move on to the next slide. So let's move on now. Okay, so this is another example. This is another example. I'm going to leave this to you also, but I'm going to address this example E. We have NO2 minus going to NO3. Okay, now on both sides, we don't even know what's the oxidation state of nitrogen. Of course, oxidation state of oxygen we know, so we are not concerned about that. Our concern is oxidation state of nitrogen. So what's the oxidation state of nitrogen here? I don't know, but I know I can find out, because nitrogen now, if I say is X, equals to plus, oxygen is minus 2, and there are 2 oxygens, so that's times 2, will be equal to what? Minus 1, which is the charge. Okay, so if I do the math here, have x to be equal to this minus 2 times 2, that's minus 4. Take minus 4 to the other side, it becomes plus 4. So minus 1 plus 4, minus 1 plus 4 is equal to plus 3. Okay, so it means nitrogen on this side is plus 3. Nitrogen on this other side, if you calculate it correctly, it will be plus 5. So it means that oxidation state is moving from plus 3 to plus 5. So if it's moving from plus 3 to plus 5, it's moving from smaller to bigger, so it is oxidation. It is increasing. Increasing is oxidation. So when it's reduced, we say reduction. But again, in reality, though it is increasing in number, what's actually happening is that it is losing electron. Oil rig, oxidation is lost. Okay. Now, so difference in oxidation state is, find the difference. Don't say 3 minus 5 minus 2. No. Just find the difference. Okay. So the difference is that we can say 5 minus 3. Always use the bigger one first so that we can just get what is the difference. 5 minus 3 is 2. So difference is 2. So we know 2 electrons will be added to the right hand side, because it is what? Oxidation. And it makes sense again, because you see NO2 minus means there's minus 1 on this end. Is that not so? Sorry, that the oxidation state on this end, we've calculated, we said it's plus 3, Abby. So nitrogen is plus 3. While on this end now, nitrogen is what? Plus 5. Plus 5. So if we have 2 electrons here, it means 2 times minus is minus 2, plus 5 minus 2 is plus 3. So again, it is balanced, and that's the correct way to write it. But we're having another challenge, is that oxygen is present in both sides, but in different amounts. How many oxygen do I have here? 2. How many oxygen do I have here? 3. So it means I'm lacking 1 more oxygen here. So how do I make up for that 1 more oxygen? Is by adding 1 molecule of water, because I need just 1 more oxygen. So 1 molecule of water to this side. How do I make up for this hydrogen? How many hydrogen do I have here? There are 2 now. So I add 2 hydrogen ion to the other side of the equation, and then the equation is balanced. I believe you can lay your hands upon F, upon D, upon C. Make sure that you solve them, you understand them before you move on to the next slide. Now I'm going to be solving this one as the last example under this equation, seeing how to balance both the charges and then the atoms. Most in this case now we are looking at oxygen, which is what you commonly come across, because oxidation, when oxygen increases, oxidation has occurred. When hydrogen increases, reduction has occurred. So from here now, I have arsenic oxide on both sides, but with different charges. If you calculate this, this will be 2x, because there are 2 arsenic, which I'm looking for, which I don't know, arsenide. So this is 2x plus oxygen is minus 2. Minus 2 times 3 is minus 6. So let me just put minus 6 directly. It will be equal to, this is a neutral atom. You can't see any charge here, so it is equal to 0. Okay, so is equal to 0. It means 2x now is equals to minus 6 going to the other side will become plus 6. Is that okay? So divide both sides by 2 to get x. So it means that x will be equals to 6 divided by 2, that's plus 3. So it means on this side, arsenic is plus 3. If we do the mass for this side, it is plus 5. So since we know the oxidation state is moving from plus 3 to plus 5, we also know the oxidation difference will be 2. So it means 2 electrons, since this is also going from smaller to higher, this is oxidation. So we add these 2 electrons to the right hand side. Okay, so we're adding 2 electrons to the right hand side, but take note of this. The difference in oxidation state in this case is 2. So 2 electrons as the right hand side of the equation. So total electron equals 4. Okay, in this case, total electron equals 4. How do we arrive at that? Just follow me very closely. What's the oxidation state of arsenic on this end is +3. Is that not so? +3. Oxidation state of arsenic on this other side is +5. We've calculated that already. So from here now, you can see that we need we need to put, to remove 2 electrons here to balance this. So this will be sorry, this is a mistake. Sorry, this is supposed to be 2. This is what we've gotten here, 2, just like we've been solving before. So this is 2. So this will be therefore what? +2E minus. Okay, so this -2 + 5 is going to give me what? It's going to give me minus, it's going to be +3, which is the same with this. So therefore, it's 2 that will be here. Okay, so if you solve it, to balance the oxygen, there are 5 here, there are 3 here. To balance it, I need 2 more. So I have 2 water. 2 water means that I'll be having 4 hydrogen more. I'll add 4 hydrogen, then equation balance. Of course, this one, all this one becomes 2. Okay, sorry for that mistake. So now for today, we are going to be stopping there. Next class, we'll now be looking at a redox reaction, that is combining both a reduction and the oxidation reaction together. We looked at half reaction now. Reactions don't actually occur as half reaction. They occur together as a redox reaction, okay? So we'll look at how to separate them into half reaction, balance individual half reaction, and then join them together to form a redox reaction. And we shall also move on to the electrochemical cells, where we'll look at the electrodes and then the cell and electrode potential, etc. So thank you so much for listening, and enjoy the rest of your day. Kindly ensure you solve as many questions as possible. The next video on this course will be coming out very soon within this week. So please ensure that you have gone through this one and you have digested it so that we can proceed on the next video. Thank you very much for listening.